Hey there. So this is short-circuiting IoT development. There was a little bit of a title change since the announcement, but the talk is still centered around my experience building out a solar microgrid. Um, and the other examples there will be other examples that I pull from, but all of them are from the front lines, patterns that you can use. So I've never done a virtual conference before, but I guess I can now list my house as an event venue. So I guess that's probably good. Cool. So a little bit about me. Hi, I'm Dan Lindemann. If you want to follow me on Twitter or check out some work on GitHub, there are my profiles. So for this project, so I'm a senior software engineer at Very. And Very is an IoT consultancy. So they're the reason that I have a whole lot more kit behind me than I normally would. I was fortunate enough to work with Daniel Spofford and Justin Schneck on this project, and working with them is like being strapped to a rocket. So yeah, it was a whole lot of fun. So I'm a senior software engineer, and by the end of the talk, if you don't have any questions, you can always ask me about Prog Rock, my dog Bowie, or renewable energy. So I have to make a couple of assumptions about you. Every time I make a talk, I make some assumptions about who I'm giving the talk for. At first, I earmarked this one as advanced because I really wanted to go super far into the weeds, and we do. But as the talk progressed, I realized that it was more and more about development patterns. So whether you're new to Elixir, new to computers, consider yourself just a web dev, or like you remember when Erlang was brand new, this talk will be for you. I also assume you probably have some fledgling interest or a complete interest in IoT, and maybe just the talk about renewable energy was interesting enough to get you in the door. So if that's all you're in the right spot. So I was hoping to kind of get a little interactive here, but I would say most people would identify as full stack, or many people identify as full stack. And so on the left, we have what's the typical full stack. At Very, since we're an IoT consultancy, we basically took the full stack of operations, front end and back end, and then we just stretch it out to include hardware, firmware, mobile apps, and machine learning pipelines. So this talk is going to focus largely on the lowest portion of the stack. So I've circled it down here, which is going to be hardware, firmware, and how you might talk to those as a software developer. So I think if you're a full stack developer, a really good habit to have is to be conversant with your neighbors, right? So some examples of that, if you're a backend engineer, right, you design your applications such that they accept external configuration, like environment variables. If you're following 12-factor app, you have different environments and you might deploy different things. And so you're ops aware when you're putting together your application. Or let's say you're a front-end developer. You know that you should make as few requests as possible, and you shouldn't ask for everything, but just what you need. So that's a front-end person being conversant in what the issues and constraints are on the back end. If you work in reliability or operations, you might build out log aggregates to help your back end and front end observe their infrastructure and help them debug problems faster. For us, we're going to be focusing on learning how to become conversant with firmware and hardware. I would love to cover this whole stack, but I don't think that I'll be given enough time to do that. So without any further ado, let's get going. So we're going to head to two main places today. Like I said, I'm going to be talking about experiences that and lessons that I was able to pull out of working on the solar microgrid project. It's only one part of a much larger system of components, but it's very ripe with lessons. So we're going to challenge your assumptions by showing you that you didn't make any assumptions at all. And then next, we'll talk about how hardware is like software. But the problem is you'll be really disappointed that I just told you stuff that you already knew. So let's start where every NERVS project starts, which is mix NERVS new hello. So I hear this problem statement a lot from developers first starting to deal with hardware and firmware. Well, I hear it a lot in my head anyways. So you might be tempted to think when you get started that you need hardware. And what I'm suggesting is that you'd be wrong. So when you first start making something, let's say you even want to do Blinky, which is the firmware equivalent of Hello World. You're just going to blink an LED. You might buy some things, get a breadboard, some jumper wires, but then you can't remember how to read a resistor, and you don't remember which leg of the LED is the right way, and you don't want to burn things because fire is really bad. And this is really frustrating. Whenever I'm really frustrated like this, my stomach gets really hot. So you might be tempted to be like, heck it, I don't need this. I'm going to go back to Phoenix or whatever you're using Elixir for already. But what's happening here is you're letting kind of like a notion of needing hardware inform too much about your software. So what you really mean to say is, I don't have hardware, and you think that that's a problem. You may be wondering at this moment, what is me telling you, well, don't worry about needing hardware, have to do with the hardware and firmware and software that I developed? Well, when you're learning a new language or learning to speak to hardware and learning to write hardware, you need little wins. So let's get one. The first thing that you're going to get wrong is you're going to assume that it's something I call the for versus on assumption. So people will think, if I develop for a Raspberry Pi, that I need to develop on a Raspberry Pi. That will certainly become true. But this one is actually it's got a really nice web developer translation, which is, just because I develop for prod, that doesn't mean I develop on prod. At least most of the time I'm not doing that. So if you're familiar with running IEXS Mix, that is a huge step in getting working and running on building a solar microgrid. So when we were doing the development, a majority of the development time targeted our Macs. So we were building the application on our local host. So maybe you don't believe me, sure, fine. Just in case you haven't seen a NERSC project before, this is a weather ball. I'm from Grand Rapids, Michigan, and this is like kind of a semi-famous thing where we have a giant colorful blinking ball that's kind of north of the city a little bit. So here I'm running IEXS Mix. I haven't hooked up any LEDs. I haven't hooked up any even networking on my Raspberry Pi or anything. There's no Raspberry Pi anywhere. But I'm running NERSC on my laptop, and I'm iterating on the structure of the application. And you can see I've already got most of the business logic implemented. So it's a small win. But once you move past Hello World, the skill is still applicable. While we start developing the application, that's actually buying our electrical engineer a lot of time to put together a lower cost custom solution. He can check out different processors. He can check out they can check out different processors. They can check out different components that we might want to work with, new sensors, things like that. And then we eventually do start developing on a commodity piece of hardware, but that's something that kind of comes all, both bolts and batteries included. So again, the majority of development is not on those hardware parts, but that's on the application logic. If we're going to translate from the web world, you really only like mangle and connect the database and startup logic like one SISH. Most of the time you develop on your machine, Mix Phoenix server, and you're writing business logic. And that's kind of like the sweet spot for developers to be in, right? It's just focusing on business logic and not really so much worrying about, well, how, what drivers is the database using to connect? So firmware is disappointingly not that much different. So again, if you're tempted to think that this approach only lasts when you're scaffolding your application, that's not true. It's actually just a really great practice that cuts down your iteration time. So your problem statement of I don't have hardware becomes I don't need hardware. And that's actually a really good thing to do. So what are some of our takeaways, and what are the patterns that you can follow to not need hardware? Because after a while, you will eventually get your hardware and your breadboard or your LEDs, your resistors, right? So when you do, there's two patterns, but they should seem very, very familiar. In Elixir, mocking is typically done with a library called mocks. If you're not familiar with it yet, you probably soon will become familiar with it. It is one of the larger and more popular libraries. It's used for mocking out modules and you'll use it in tests, and it's great. We found that we needed a little bit of a stronger contract. So we developed a thing called Hook, and Hook is somewhere like Mox and Pact kind of mixed together. It allows us to create a hardware abstraction layer for runtime, as well as stubs for testing. So other things that you will look for in this space are nerves-friendly libraries, or firmware-friendly libraries, I should say, that also might include a stub implementation. I want to give a shout out to the Circuits GPIO team for not only including a stub implementation to use, but for including it in like the top level README when you're getting started with the library. It's also helpful because even there are non-really like things that you don't think about when you think of hardware, like VintageNet, right, is one of the most popular networking libraries for embedded development in Elixir. And VintageNet assumes that you're running on Linux because it's intended to be running on a NERVS device, which is Linux. So we'll see how we're going to scale that up in a second and figure out how to run it on host, because when I refer to my host, I'm referring to a MacBook. So the next pattern that we look at too that kind of emerges, it's very related to Hook, is abusing or using or leveraging config.exs. So you probably already do this in most of your projects. You'll have a dev, you'll have a prod, and when you set the mixenv to be, one or another, your application will pick up what is appropriate and run with those. So a common one might be your database connection for dev would be against MySQL, or maybe a local host Postgres, like a Docker container somewhere. And then in stage or prod, you might have your actual database credentials being fed in through CI/CD. So it's slightly different from the way that we normally talk, only in that what we're doing here is we're pulling in fake hardware components. So we want things that behave and look quite a bit like the hardware modules will look, like the real implementations do, the real libraries. But we don't want them to be trying to raise the voltage on a GPIO. First of all, because my Mac doesn't have one. So we developed something called a hardware abstraction layer, or a HAL. And we do that by providing a mapping to Hook inside of the config. So what we're able to do is to map the modules that we are going to call in the hardware abstraction layer, and we're going to reference them based on the environment to either their hooked version, so something that's appropriate for my Mac, or something that's appropriate for the actual device. I think we also call it HAL because people like referencing 2001: A Space Odyssey and just saying, "I'm sorry, Dave, I'm afraid I can't do that." But that's just a theory. The key takeaway here is that both of these are allowing us to stay in business logic development and abstract away the need for hardware. So let's do a little bit deeper look at Hook. So it is something that you use because it's going to expand this this function called Hook, which will allow us to dispatch. If you're familiar from the like JavaLand or somewhere else, this looks a lot like dependency injection. And that's essentially exactly what we're doing. We're saying, what's the appropriate library to be running here? Go get it. And so the code doesn't look very much different other than you're saying, Hook, find me the right thing. So all of this is mapped together in config.exs. So how else can we use that? If you don't need full-on Hook, something that you can do here is leverage config.exs. So here's a portion of our application that's responsible for getting the system information. So we need to know about the CPU utilization, the disk utilization, memory, and network. This is the directory layout for system info, and each of the top level CPU.ex, disk.ex, memory, and network, those are going to be choosing between host and target. To belabor the point, even on my Mac, there is a way to get this information. For example, how much disk I have remaining, but it's not the same as the one on Linux. So even on like not special hardware, this pattern is very, very helpful. So just to recap, develop local to speed up iteration time. Abstract away the hardware layer as soon as feasible. So let's think back to that system info module and start to wonder, like, why do we even care about this information? Well, to help us solve a problem or two. So the solar grid controller, I haven't talked a lot about what it is. What our application does is it sits in the middle of an array of solar panels, and it's going to collect utilization information from other solar panel meters. So it's a microgrid, meaning that you're not connected to the major grids, and you are creating a utility of energy. So you want to know which panels and which meters are generating electricity and which meters are using electricity. So all this data comes into our module, and our module is responsible for sending all of that information back up so that it can be processed and bills and payments can be paid, and we can make sure we have a good accounting system. But the problem is if you're on a microgrid, the places that these are deployed are very remote parts of Africa or Canada or Australia. And so you don't have the internet. You might not have it for a couple weeks. When you get it, it's probably not fast or super reliable, like somebody's bringing it in on a backpack through satellite. Another problem is that we're running out of space, right? We're just like a small device, and we have to be responsible for all of the utilization information for this grid. And we can't really lose any of it, because if we lose data, then that means that the grid operator can't collect money. And so the whole kind of operation goes kaput. So the scary part here, right, the part that makes me uncomfortable and makes most new to firmware, new to hardware developers uncomfortable, is that you might think that because you're deploying to a constrained environment, that you yourself are constrained. But that's something that you're going to get wrong, because in Nerves land, we build on top of Buildroot Linux. So you might be thinking, I need some archaic C libraries, some ports or NIFs. We did load a Rust port for talking to the solar panels. But in general, for the system info module, we used plain old Linux utils. So if we need to know information about the system's disk utilization or network, we would either use df or cat out the contents of procnetstat. The nice thing about Buildroot is that if we ever need more than this, we can use as much or as little of Linux as we want. But just the takeaway here is to not forget that the simple stuff is there. For a little while, we did experiment with bigger utils, so bmon and vnstat. It's not super important what they did, so much as it is to know that if you need to step out of the little sandbox, you can just make a bigger sandbox by rebuilding Buildroot and adding that new dependency to your target. So if you want to know what the experience is like, if you have any developers on your team, or you yourself like to add .sh files like scripts to your repository, imagine it's like you're running that and all of a sudden you run some script and it says command JQ not found. What's happening here is that your system hasn't installed the correct dependency. And so you'll just need to brew install or choco install JQ, and then the script will work. It's also very similar, for my money, to developing a Docker Alpine Linux image where like curl and make are not available. But yeah, so if you don't believe us still, these are honest to goodness implementations of how we answered network and disk utilization in our firmware. So you're seeing a file read and you're seeing a system.cmd. And you might be thinking, you're just reading files and doing regex. This isn't like, there's no special thing here. We're not talking to a driver. We're not reading binary or like streaming whatever. And you're totally right. I 100% agree with you if that's your thought process. So it's just like when we write JSON, parse user input, or save files to S3. In firmware land, it's pretty much the same, but a little bit different. The key difference for firmware land is that you are aware that you're on a computer. I know that sounds kind of funny, but in web dev land, you can make a bigger EC2 instance or something. But you can't download more RAM to embedded systems. You pretty much are stuck physically with what you have. So just being aware isn't really a constraint, because we're allowed to choose which things we're aware of by increasing the size of our sandbox, or using all of the things at our disposal in normal Linux, which is a lot of things. But here we can use this information to take actions, right? To say, how much data should I send? should I be running a compaction or a compression on our database? What messages are highest priority to send? So all of this information can be used because we know that we're on a computer and we're using like the regular power of Linux. I do really wish that the recommendations here were cooler than like use Linux and develop local. But I mean, I think that's kind of cool. So all the things you get wrong in non-firmware development are the same things you get wrong in firmware development. Best practices are best practices. IoT development is just software development in disguise. So far on our journey to become conversant with hardware, we've learned that we are only as constrained as we think we are and stand on the shoulders of Linux. And you don't want to talk, you don't always have to talk to hardware. And in fact, getting hung up on needing it will probably slow you down. So we can get around the things that go wrong, but we're about to introduce hardware into the mix, so hold tight. A while back, I had developed a personal library system. So I like the Grand Rapids Public Library. Like when I say library, I mean books, not software. You can check in and check out your own personal library collection. So I wrote it in Python, and I talked about this at several Python conferences. When I built it, I noted that I used Python to figure out if my hardware would work, because I'm a little bit faster in Python still, sorry. But I was going to be building an eventual Elixir project. I also noted in that project that I was pretty disappointed with how the software architecture came together and worked out. So what had happened with that project, the reason the software was disappointing, despite me finding out that my hardware was going to work together, was that either I didn't know a firmware architecture pattern for it, or in that case, my language made it difficult or not obvious. There are some assumptions baked into Python that make things a little bit harder than they might be. So what happens when you finally do get around to it? How do you structure this application? Well, it turns out processes. Processes are a honking great idea. So let's revisit that RFID application and kind of compare and contrast how we might do it in Python land versus how we would do it in Elixir land. So the issue I had in that application was sharing. Flask, if you're not familiar with Python, Flask is kind of like Phoenix, but a little bit smaller. And MFRC 522 is a library that talks to an RFID reader for you. Both of them hold a complete, like they assume that they're the only thing running. And in the case of the RFID reader library, it holds it in a literal while loop. So the way that I got around this was breaking out of the RFID reader loop, like literally break every quarter second or so and letting Flask take over the context again and then jumping back in a little bit later. It's really clunky, but I did suppose that the right way to do this, because I've worked on firmware things before, would have been to wrap, instead have the web server be an async one, like instead of Flask, use Quart, which is an async version of Flask, and then have MFRC 522 live in its own process, and then maybe use Redis PubSub to coordinate between the two. Kind of like a message passing, but that's a lot more development. So in Elixir with nerves, we can use processes. They're a really convenient model for modeling firmware as well. So here's how we probably would have done it in nerves. We would have put Phoenix run as usual in its own process. Great, it's the Phoenix server. And we would use circuits SPI and wrap the appropriate parts of that in a gen server and call that process, book appearance or reader, right? We would abstract it out to some business logic idea. And then we'd be able to coordinate them, if a book gets checked out and we see something on the pad, send it over to Phoenix. But you already knew that. So it turns out this is actually how we ran the configuration server for our solar microgrid. We had an admin application that was responsible for handling some configuration setup, but it's the Phoenix application running on nerves. We also had a reset button, like a physical reset button, and tamper detection tied to GPIO. And the one I mentioned earlier, we had a Rust port wrapped in a gen server that's responsible for talking to the solar meters. So notice though that these two, the reset button and tamper detection, are not like in some big GPIO module. Instead, they're in a reset module or a tamper module. So what's really cool about using processes is you can grab the parts of hardware that you need, right? GPIO in these two cases, and you can present a layer to the rest of your application that it's appropriate to pass messages to. So the cool benefit of that is if we have a reset module, right? And normally it's tied to a GPIO press. And it has a lot of logic to make sure the application shut down, the database is down first, and then we're all good to go, right? But let's say we wanted to provide a software reset. We actually did do this. You can now pass a message from Phoenix saying, hey, the user wanted you to do a reset. And you can call the reset module. And instead of having to use circuits to interrupt you, to have a GPIO be brought up or brought down, you can now add software reset to your admin application. So that's a really nice thing to do. It allows us to reuse some of our modules, and it allows us to kind of create new and interesting compositions of them that aren't just tied strictly to a piece of hardware. So in sum, leverage your hardware abstraction layer in business logic processes, and be grateful for message passing. Some people have to use Redis. Right. So now we're really moving, and our hardware has just arrived in the mail, and I'm sitting there. I've got a PDF on my screen of all of the hardware specs, which is another problem. So when I add this new piece of hardware and I'm looking at the specs, I tend to stare at them for hours. They're very hard to read sometimes. But what's happening here is that I'm believing that these are sort of ground truth, and everything in these documents are meant to be taken at face value. And the problem is that I'm making the assumption that engineers write docs that tell the truth. I spent the first part of my career as a manual and automated software tester. I'm not sure who first said this, but I think it's probably one of the few truths in software engineering. So the second thing to learn about hardware being software is that the docs lie. Of course, we should know this. Hardware used to be called, well, before hardware had software on it, hardware used to be called whatever it was. So if something was a calculator, it was called a calculator. If it was called a loom, it was called a loom. So we can kind of follow a chain of reasoning, which says if software came from hardware and software docs lie, like surely we must know that our forebears, hardware, docs lie too. If you have the sort of retronym like hardware and software, you can assume that one idea from the forebear sort of translates to the newer, to the successor. Just like acoustic guitars used to just be called guitars until electric guitars came in and sounded sweet. We know what to do when we're trying to learn a new piece of software. Nobody, or very few people probably, look at the compiler of a programming language and understand it completely. Very few people can look at the syntax and have it memorized. That isn't how human brains work. So what do you do when you're learning a new language, right? And we're learning how to speak to hardware, so we're learning a new language. You write hello world. You write hello world 2, hello world 3. And you do it until you feel really comfortable with the language, and you try out new parts and new features of it while you're going. The same thing also applies with libraries. So when you're taking in some new dependency, you write tests around it, right? You say, okay, well, I think it'll work this way. And so hopefully, the S3 module gives me the file back in something that's reasonable. So you use it and you test it. So I think we should just update this quote to be more inclusive. So the 3 kinds of lies turn into lies, damned lies, and documentation. So as your hardware system grows, the model you should hold in your brain is to think about each piece of hardware as a new dependency. So whenever you add a new library to your code base, there is some time, there's a lag between when you add it to mix and when you fully understand how the library works. So if you're working in your regular software development lifecycle and you start adding dependencies and you trust the docs are perfect and you understood them completely, and that's kind of a big caveat, you're setting yourself up for the big bang. The big bang is what happens when you add 2 or more dependencies at the same time, and you assume that they'll play nicely together. I know for me, Ecto didn't work the way that I thought for a while, and now I get it, or at least I get it a lot better than I used to. Or like HTTP Poison. I don't know if you can trust yourself to read the docs and have a complete understanding of something, that's a special gift. But for my money, most of the time what happens when I work with something new is I add patches or adapters. In hardware, you don't get the exact same benefit. It is kind of funny though that the word patch does come from patching, like a patch cable in hardware. I think it does. Somebody can correct me on the etymology of that on Twitter later. But we do get to correct hardware with patches, but things just take a lot longer to do. So the overwhelming reason it's important to treat this turnaround time as like a sacred time and move slowly when you're adding dependencies in hardware is the turnaround time on patching is not seconds or minutes like we're used to. It's on the order of hours or days. And so there's a really, really compelling reason here when you're, adding, to your mixed depths file Ethernet or Wi-Fi. So if you think about it like this, it kind of makes a lot more sense why you would want to take it slow and explore one hardware module at a time. So how might you actually do that? So at Very, we have a hardware development process where we build out the smallest possible hardware with the smallest possible software, and then we iron out the kinks. So we have a custom PCB printer that allows us to spin up test harnesses or compatibility harnesses so we can work on each little component in absolute isolation. And then eventually, as we start adding things on and that feature matrix starts to grow and the complexity matrix starts to grow, we have a lot more safety as we're going forward. So to translate some of the things that go wrong in hardware to a more software-oriented world, hardware components have tolerances for electricity because that's how they run. Think about this like an undocumented API request limit or like a max page size that nobody ever told you about, but it's only going to give you 100 documents no matter what. Hardware components sometimes also need step down and step up to change their voltages. I kind of think about this like custom JSON serializers. It used to be in the bad old days that Python running Lambdas in AWS running Python needed a special adapter to serialize the JSON appropriately. But you can imagine any other adapter that you've used before that said, oh, well, I thought it was going to return a list, but it's actually a list of lists. So I need to just pull that intermediary one out. So in your journey, it might take you a long time before you buy something like a custom circuit printer. They're like $4,000 each. But the same process and the same way of thinking about things still applies even with a breadboard or a soldering gun. Principle's the same. Take your time, add one dep at a time. Cool. So I hope I've given you some tools for thinking about firmware and hardware today. I hope you feel inspired by how few barriers there are in order to get started and to do things right. At ElixirConf, we happen to know and like a language that makes the really, really hard stuff a lot easier than other folks. So let's use that. And again, we're going to understand here that we are a lot like Freddie and that we've unmasked the stuff you already know from software development is the same best practices for hardware development, but maybe you didn't know it. And we would have gotten away with it if we weren't for meddling devs. Thank you so much for your time and attention. Every day you only get so much of each, and I can't tell you how much it means that you've given me some of yours today. I also want to throw a thanks out to my colleagues, Jen, Justin, Daniel, Emily, and Veronica. Y'all are the best. So yeah, thank you so much again. Also, if developing solar microgrids sounds like it might be your jam, Very is hiring, so come work with me. That would be super cool.
Perfect. Well, thanks again, and see you next time.